Okay. There we go. So I was specifically asked to talk about simulations. So all the observers can safely go check their emails when they can ask. There's nothing really useful. So unless we're trying to model something that the radiation field is actually the main player, and we actually don't want to include an RT solver in the code, because RT solvers are quite expensive. There's photons move with speed of light, unfortunately, so it makes time steps very short. It turns out actually that we also do not need to read. Because, for example, if we don't care about realization, we don't actually want to study realization. Realization by itself doesn't affect star formation in galaxies. Sometimes you hear that yes, it suppresses star formation in dwarf galaxies. It's actually wrong. It's a different story.
You're the one that told us that.
So that was wrong. Yes. So it actually doesn't affect galaxies. It does affect gas inhibitors. So there are actually three different processes which do explicitly depend on the local radiation field. It's the formation of molecular hydrogen, it's cooling and heating rates, as Sebastian showed us, and of course radiation pressure as a feedback mechanism. So I'll talk about all of them briefly. So for H1 to H2 transition, there are actually several models exist in the literature to help you to put this in the simulation. They're all mutually compatible, so you can choose whichever one you like. And so in this sense, it's easy. This is done. You don't have to follow any radiation field or anything. This is done for you. And we need to do it because molecular gas determines star formation rate, right? And atomic gas does not. So you've already seen lots of Koenig-Schmidt relation. This is Koenig-Schmidt relation. That's how it should be shown. And we know that star formation rate correlates strongly with molecular gas. It doesn't correlate at all with atomic gas. So there's actually no justification for plotting star formation rate against the total gas surface density. This is just a side note. Because whenever you're just plotting total gas, what you're doing, you're taking some real physical dependence and adding noise. And of course, if you have two different quantities and you add enough noise, you can match them easily. So in order to understand, to model star formation, you have to model molecular gas, but as I said, it's easy. This problem is solved. Right? You don't have to follow complicated molecular networks. It's been done for you already. There is one small correction that I want to advertise using this opportunity. For all models that existed up to now, there was one small effect that wasn't actually included, and that's an overlap of damping rings between lines in Lyman-Venner band. So this is Lyman-Venner band, between 9 and 12, and going to 10, 30 something, so it's part of it. And those are all absorption lines which correspond to different levels of hydrogen molecule, and photons which hit those lines can destroy hydrogen molecules, so we want to shield them. At high enough column density, those wings of those lines begin actually to overlap, and the lines start helping each other. That's an effect that has not been accounted for. It's only important for really low dust abundances or metallicities. So it's something for galaxies less than SMC, for example, that becomes important. So overall, it's again a small correction, which is not crucial. And the dependence of this transition on the radiation field is actually weak. So formally, it does depend on your ultraviolet radiation, but it's only logarithmic for galaxies like Milky Way and galaxies with high star formation and strong radiation fields. So in a sense, we need to know very roughly what the radiation field actually is. And if we go and look at high-redshift galaxies, where most action happens, there the radiation fields are in fact substantially higher than in the Milky Way. Which means that it's even less sensitive to what the exact value of the radiation field is. So H1 to H2 transition is very, very forgiving for not knowing the radiation field precisely. Now, its cooling functions, it's more severe, as Sebastian showed us, and I'm going to give a very brief cooling function 101. And the rate of change of total energy from the gas, the heating and cooling functions come with different signs, they always come together, you cannot separate one from the other. And in general, it depends on temperature, density of the gas, abundance of different chemical elements and different ionization species, and actually different excitation levels, depends on the radiation field and the opacity of each of those levels. So we try to do it in the most general case, it's a nightmare. To do it exactly, you need something like cloudy. That's why we use cloudy to compute it, but we are not there yet. We cannot actually include cloudy as a subject model in the simulation. And if you do it, then you'll be able to run 4-cube simulation at most.
Cloudy assumes equilibrium.
And cloudy assumes equilibrium, right? So if you want to do it non-equilibrium, it's in the this is actually, right, in this case, this is more general. It doesn't assume any equilibrium. So then, what we usually do, we assume equilibrium, and we assume optically thin, so we throw away orbitals, and we assume excitation balance, equilibrium. So in this case, the cooling function becomes a function of temperature, density, metallicity, and radiation field. That's what we often call cooling function. It's actually wrong. If we had a mathematician in the audience, he would say it's not a function. It's a functional, right? Because it depends on the arbitrary function. A function which depends on a function is not a functional. It's a functional. So this dependence is very difficult.
You can tell you studied in Russia.
And this dependence is real. As Sebastian showed you some example. I actually have something very similar, just was too lazy to remove it in the last 5 minutes before my talk. So I'll show the same animation, almost the same animation as he showed. This is the cooling function, it's blue, heating function is red, dash is a metal free, solid is solid metallicity. And this is radiation field, this radiation parameter in some particular units. And so you can see how in crank radiation field, how the heating and cooling functions actually change. And so the first thing that happens is start losing hydrogen in helium peaks. It's also the easiest to ionize. But the metal peak, like this one,
This is solar.
remains for a little while. Huh?
You're at solar metallicity.
The solid line is also metallicity, dash one is metal free.
And what's the shape of this invasion background?
But I don't have a plot of this. It's a little bit of X-rays, mostly stars and a little bit of cosmic background. So you get to really high radiation fields. You essentially wipe off everything except branch traveling, and the heating rates become very large. And you can cook up some interesting cute examples. For example, like this one. This is a cooling function without any radiation fields. It's collisional cooling curve. It's collisional ionization cooling function which doesn't apply anywhere in this universe. And this blue and red again cooling and heating functions when you put a quasar in the middle of its scale and let it shine. When the quasar shines, it actually ionizes over its scale and suppresses cooling throughout. And so it's similar to what Sebastian showed. In this case, you actually have a quasar, it has X-ray photons. I said, however, this is equilibrium, right, where the lines intersect are however unstable. So whether the cooling actually happens or not in this case is an open question. You need to know how this instability will grow, if it grows at all. And of course, the quasar will only do it for 10 million years, and then it shuts down, and you can go again. So what do we know about these local radiation fields and the cosmic background? Actually, if you look at the simulations, if you do put radiative transfer solve in your simulation and try to run it, then you can estimate what's called the proximity zone, and the regions around galaxies where local radiation field dominates. That depends on frequency. So what I show here is the proximity zone for hydrogen ionizing photons. And if you add soft X-rays, Sebastian talked, it will actually move out because the absorption will be smaller and escape fractions will be larger. But in general, they're actually quite small. For hydrogen ionizing photons, for normal radiation from young stars, they're quite small. And at the redshifts where most of the action happens, it's only really the ISM of the galaxy. There are fields, local radiation fields. If you move a little bit outside, okay, it's actually cosmic background that dominates. And you know how to do cosmic background. Right? It's 99.99999% of the volume. If you include the soft X-rays, okay, it becomes one of those lines disappears, but it's still 99.999. And if you know how cosmic background evolves with redshift, we have a model. There's this dependence on the function, this kind of dependence on the redshift, and this four-dimensional table you can tabulate, parameterize, etc. That's been done many times. I think the best and most useful visualization and tabulation is actually by your open people. So that's it, easy to use, and so if you actually need to do it, that's what you should be using. And then we can talk about the rest. So the rest 0.0001% of the volume actually not matter for the following reasons. Whenever we model stellar feedback, we actually never model feedback separately. If you come here and say, I am working on stellar feedback, you're actually wasting your time. Because you should always work model staff formation and feedback together. They are both subgrid models. They always come together. And one example of this is here. This is a plot from a recent paper by Andrei Kravtsov and Oscar Agertz. There are similar plots in different other papers, and what they showed that if you have complicated model for the feedback, very efficient staff formation, then you get this black line, which roughly corresponds to the star formation history of the Milky Way that Peter tells us the Milky Way should have. And so you need strong feedback to do this. And all I can do, I can play a simple game and just change the star formation prescription. And I make the feedback weak, the standard, relatively weak. It's not really weak, but it's not strong as in Kravtsov and Oscar and Agertz paper. If I keep the same star formation model and just use standard blast wave prescription, it's actually a very well-known fact. Blast wave model doesn't actually work very well in AMR codes. It works in a stage code, it's much better, but it's also a question of resolution. But then if I change the star formation model and keep this feedback, I reproduce their results. So if I change my star formation, I have to change my feedback. They always come together. Right? If you change one, you can compensate by changing the other. And that's what we actually do. So we always model them together, except that people often don't vary this path. But in principle, we should, because we don't know what the star formation recipe actually is in reality. But if you follow this logic, you can actually add cooling here. And try to model everything together. In fact, that's what actually we do. So when most of the outer formation simulations assume cooling function, nowadays it's cosmic background, but it's a fixed cooling function, which actually doesn't depend on local radiation fields. Then we do star formation, we run and do the feedback, and we try to make sure the galaxies look reasonable. So if this one is off, you can always compensate it by putting tens and knobs in other boxes. So in some sense, that's what we are modeling, and maybe we don't need to count radiation field in this case, but if you're really stubborn, and you really want to account for the radiation field somehow, you just want to boast to count, I am accounting for the radiation field. There is this trick you can do. You write the equation for data transolution, which is the equation for data transfer. And you say, well, in my first approximation, what tau does, it lets my photons travel over the mean free path, and then don't go beyond that. And so if you know mean free path, in the first order, you deploy this integral from 0 to lambda without any tau, and it is nothing else as properly weighted average star formation rate density times the mean free path is actually surface density of stars. So in fact, when these galaxies evolve, they work as radiative transfer solvers. All we need to know is the surface density of star formation within the region or size of the mean free path, and that's your typical radiation field at a random location in that region. And that actually can be done very easily in modern codes. All you have to do is to use the tree structure. You're using AMR, you're using SPH. All you need to do is take your star, find the sphere with the radius mean free path, find in which cell this sphere intersect, and the number of young stars in those cells is your radiation field. And it will not be very precise, and if you want to do it really better, you can weight different cells with different weights, but you will get a pretty decent estimate of the star formation of the radiation field in the typical location in your ISM without doing any radiative transfer.
Is your mean free path computation adaptive?
Well, again, those are details. I'm just sketching. Yes, in principle, it has to be adaptive. Right? In principle, you have to iterate that the mean free path is computed over this region. And again, if you want to be really sophisticated, you write those integrals and see how the split, and you can do it probably much more decent than the sketch that I'm presenting. But the point I'm going to make is that radiation fields are not really necessary because they do affect things that can be circumvented or that don't depend on radiation fields very strongly, like molecular transitions. And so at the end, you actually don't need to count radiation fields in the Gauss formation simulation. Right? I spent all my scientific career doing that. And I'm telling you, it's actually not necessarily necessary. It's fun, but we can avoid it, right? So it's not completely crucial. And in the worst case, if you really want to be sophisticated and have, or boast at least that you count for radiation field, then you can use this very simple formula. The radiation field is basically a star formation ring within the mean free path.
Well, I mean, what if you don't have a disk geometry, right? Because I think one of the concerns was that if you're way out of the plane.
Well, that's applies. Okay, then just use this. No. Again, if you want to be, you can just follow this and see the steps Chinese, and you can really, replace them with more sophisticated and more accurate expressions. Yes.
Well, actually, I didn't understand you include. You say don't include the radiation field. You mean don't include radiation transfer.
Well, in this case, yes, don't include radiation transfer.
Transfer, not field.
Okay.
And second thing, I completely agree with you, but this depends again on which frequency, which part of the SCD you're looking. If you're looking X-ray, is also not important, so we don't have to include it.
Well, this for example, with frequency explicitly, just the mean free path will depend on you. So you might have to walk up and down your tree. At different frequencies, you walk higher or lower. But in principle, you can always do it this way. But even that is already maybe too detailed for most of our simulations today, because if you just live in this regime, then maybe you don't have to worry about it at all.
Yeah.
You just compensate it by feedback.
Yeah, I know for another way. The mean free path at the X-ray bar is so large that you don't have to include it anymore, because the mean free path is very large, given the X-ray.
Well, that must depend on the frequency, right? And then it depends on the weight in which redshift, depends on what the cosmic background is doing. So
yeah, I'm just saying that it's only when you're close to the lambda.
it's not necessarily, well, right, but remember, it's not only the mean free path that matters, it's also the proximity zone that matters. Because if you are dominated by the cosmic background, you don't need to do any radiation transfer, you just take Wier's pooling functions and you are done.
I'm just with you, I also think you don't have to include it. So I imagine some other reason why you don't have to include radiation transfer if you're interested in it.
Hard X-rays.
Or,
So that's all I wanted to say.
I guess there's some more questions, so we'll take you up here.
I think you have to distinguish between dynamics and diagnostics. The
For
dynamics
diagnostics, it's separate, yeah, I agree.
the diagnostics is much more important typically than for dynamics. Radiation.
Well, okay, I would probably disagree with it.
For example, for the circumgalactic medium, for example, the radiation, even if it doesn't change the
But-
dynamics very well, it can certainly
If
change.
your dynamics is not affected, then you can do all your diagnostics in post-processing.
That's true, but with then including radiation and post-processing. But I can,
Oh no, but that's easier, right? So
Yeah.
radiation,
Yeah, that's-
it's your analysis. Analysis you can do whatever you want. It's just running the simulation is artificial when it is a train.
You also said that realization is unimportant for galaxies, which I
Assessment.
thought-
Ionization, yes, it is not.
So
important.
why is that?
Because the galaxies that are affected by ionization contain no molecular gas. If you adopt this paradigm that stars only form in molecular gas, these dwarf ones, which are affected by photoionization feedback, contain no molecular gas. And so they form no stars. And they may still have halos with gas, without gas, but they form, if I call a galaxy a dark matter halo which contains at least one star in the middle, then those are.
But you're not saying that the heating from 10
No, the heating affects the
4
gas,
Kelvin
but-
is unimportant.
The halos which are affected by heating do not form any stars because they do not contain any molecular gas ever. right? And they're actually a factor of 10 in mass below the limit in which K will stop forming molecular gas. So within the paradigm that starts forming the molecular gas, those caves will not be affected.
Okay, so radiation is important, but not the ionizing radiation in that sense. The photo-dissociating radiation does the job for you. So you're kill it. So
No,
any radiation.
it's not the cosmic background that does it. It's a local photodissociating radiation that matters. I think it's actually more important is the fact that molecular hydrogen forms on dust, and you just don't have dust, so you don't have enough metals, you don't have enough dust, you don't produce enough molecular hydrogen.
Looks like Phil had another question.
This is sort of just connected to what you were just saying, but just taking issue with the point at the very beginning about the molecular KS law versus the total gas. I mean, I think at the very low mass end where you're below this cutoff, it's different physics, but I would say above the threshold for the KS law, I think there's a lot of good arguments from the star formation community and from people doing the chemistry that there's no causality in the correlation between molecular gas and star.
It doesn't have to be causality. Right? The correlation does not imply causality. We already learned that.
So yeah, so I think we're on the same page. We're just saying I think we should compare with both, because to the extent that star formation is set by self-regulation with gravity, you need to compare to all the gas. But
no, I entirely disagree with this. Right? So then total gas is this plus that. Right? So this correlates and this doesn't. So whenever you add H1 to H2, you're adding noise. You're adding variable which does not correlate with star formation rate. So you're actually adding more noise.
So
why would you do it? Right?
I think the point is the amount of molecular gas you get, right, is set by self-regulation on some bigger scale inside the molecular class.
Yes, indeed.
So comparing that relation, whether you compare it as a KS law, where you're admittedly, going one layer, you're hiding that in one layer, but you have to compare that relation if you want to ask, is my galaxy forming the right amount of stars? You don't compare it to this unless you know that you have the right amount of molecular gas.
No, but I said there exist several models. They're all consistent with each other. It doesn't cost you anything to make this work if you don't know the total gas. In post-processing, right, you don't need to follow this in your simulation. You can if you want, very cheaply.
I agree we should make that plot. I'm just saying I don't think we should not make the other plot.
No, I think you should not, because I said you're adding noise. You're taking the real correlation.
With no Kennekic-Schmidt law arguments, but I'm sure Phil and Nick will be happy to do a show after the day-to-day of Kennekic-Schmidt law discussion.